Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we will start a new topic on natural convection or free convection. Now, the convective mode of heat transfer involves fluid flow along with conduction or diffusion and is generally divided into two basic processes. If the motion of the fluid arises from an external agent, for instance, a fan, a blower, the wind, or the motion of the heated object itself, which imparts the pressure to drive the flow, the process is termed as forced convection. If, on the other hand, no such externally induced flow exists and the flow arises naturally from the effect of a density difference resulting from a temperature or concentration difference in a body force field such as gravity, the process is termed natural convection or free convection. The density difference gives rise to buoyancy forces, due to which the flow is generated. Here in the picture we can see the velocity field generated out of a heated square cylinder. This is a very important experiment. It was conducted by Professor Krauss in 1940 and subsequently it was published, and a very good description is available in the reference given here. This experiment was started by Professor Smith, and Professor Krauss gave a complete description. This is in the flow field that is induced by the higher temperature than the ambience of this square cylinder. Now we shall consider situations for which there is no forced velocity, yet convection currents exist within the fluid. I have already mentioned about it. They originate when a body force acts on a fluid in which there are density gradients. The net effect is a buoyancy force which induces fluid velocity. The density gradient is due to temperature gradient and the body force is due to gravitational field. The seminal contributions of Professor Ostrach and Gavert together with Professor Jaluria are available in addition to earlier studies I mentioned about Professor Smith and Professor Krauss. Professor Ostrach's book or this chapter in Advances in Heat Transfer, and the book by Professor Gebhardt, Professor Jaluria, Professor Mahajan, and Professor Samakia is an excellent documentation of various buoyancy-induced flows and heat transfer. So we will typically, focus on a heated plate, a heated vertical plate. To begin with, the focus on a classical example of boundary layer development on a heated vertical plate. In the previous picture we have shown it also. The fluid close to the plate is less dense than fluid that is further removed. Buoyancy forces therefore induce a free convection boundary layer in which the heated fluid rises vertically. You can see the heated fluid rises vertically. Entraining fluid from quiescent region. The resulting velocity distribution is unlike that associated with forced convection boundary layers. In particular, the velocity is zero as y tends to infinity, as well as at y equal to 0, with one exception, similarly at y equal to 0. So here the y coordinate has to be seen. This is a y coordinate and this is a vertical flat plate. X is the flow direction, and y equal to 0, obviously velocity will be 0, but at y equal to infinity also, since the medium is quiescent, so velocity is 0. We can now, in particular, the velocity is 0 as y tends to infinity as well as at y equal to 0. With one exception, assume the fluid to be incompressible. Fluid is incompressible, but fluid has a density difference. The exception involves accounting for the effect of density variation due to temperature causing buoyancy force. And this is what is called Boussinesq approximation. That means our continuity equation need not change, but we need not change the continuity equation, but density difference is well accounted by the buoyancy force, which is included in the momentum equation. The appropriate form of x momentum equation in the flow direction, here again we can show x momentum equation is basically buoyancy driven, the buoyancy induced flow direction. We can write rho u del u del x plus v del u del y equal to minus del p del x minus rho g plus mu del 2u del y2. And outside the boundary layer, we can write del p del x is minus rho infinity g. This is hydrostatic equation. Outside the boundary layer, we can write basically del p del x equal to minus rho infinity into g. That means pressure equal to rho minus rho infinity into g into h, or the height in the flow direction. So this is del p del x, the pressure gradient coming from hydrostatics outside the boundary layer. And again, let us re-emphasize, this is the flat plate which is heated at a temperature Tw. Tw is greater than T infinity. T infinity is the quiescent fluid. Its density is rho infinity. And within the boundary layer, density is variable density, it is rho, and this is the flow direction x, velocity component lowercase u, this is the normal direction y, and velocity component is lowercase v. Now if we substitute equation 2 in 1, we will get this form: rho u del u del x plus v del u del y equal to rho infinity minus rho into g plus mu del 2u del y2. Now we introduce this volume coefficient of expansion beta, which is given by 1 by original volume v del t, temperature driven volume change, volume change due to temperature difference at constant p. So we can write beta equal to 1 by volume infinity v minus v infinity divided by t minus t infinity del v del t, equal to, we can just perform this algebra, rho infinity by 1, rho infinity minus rho divided by rho into rho infinity 1 by t minus t infinity. This is simply, v has been written by 1 by rho, v infinity has been written as 1 by rho infinity, and and then this has been worked out. So beta is rho infinity minus rho divided by rho into t minus t infinity, which can also be written as 1 by rho del t at constant pressure. And from these two equations, then we can write basically rho infinity minus rho can be substituted by an expression involving beta. So rho u del x plus v del u del y equal to rho minus rho infinity is basically beta into rho into t minus t infinity, and g was there, so it becomes beta g rho t minus t infinity plus mu del 2u del y2. Similar to force flow boundary layer, y momentum equation takes the form del p del y equal to 0. The set of equations governing natural convection over a vertically heated plate then becomes, we invoke Boussinesq approximation, that means continuity equation we need not change, it remains del u del x plus del v del y, but effect of buoyancy is added with the momentum equation in the flow direction, which is a vertical direction. Gravity is acting vertically downward, so u del x plus v del u del y equal to g beta t minus t infinity. Again, let us look at this equation. From here we take, if we divide this entire equation by rho, we get this g beta t minus t infinity plus nu del 2u del y2. And thermal boundary layer equation remains as u del t del x plus v del t del y equal to alpha thermal diffusivity del 2t del y2. And beta we can also write as a minus, we have seen that this is minus 1 by rho, basically del p del t at minus 1 by rho del t at p. So let us again look at it. Beta is minus 1 by rho, we already worked it out, minus 1 by rho del T at constant pressure. I'm sorry, again let me repeat, beta equal to minus 1 by rho del T at constant pressure. So we can write the expression for rho from the ideal gas, and then we can write this as 1 by rho P RT square, and then P by RT, PV equal to RT, we can again substitute here, and basically we can write this as 1 by T. So P by RT becomes rho, and then this becomes 1 by T. So beta for perfect gases, 1 by rho del T at constant pressure. We substitute the expression for rho, perform the derivative. This becomes 1 by rho P by RT square. P by RT is rho, so this becomes finally 1 by T. So beta is basically 1 by T, and this we will need while calculating beta in our calculations, in our derivations. Boundary conditions at y equal to 0, as usual. Y is the normal to the flow direction, y direction. Y equal to 0, u equal to 0, v equal to 0. Y equal to delta, u equal to 0, del u del y equal to 0. And at y equal to 0, t equal to tw, and y equal to delta, t equal to t infinity, del t del y equal to 0. So let us again look into this. At y equal to 0, we have taken u equal to 0, v equal to 0. Y equal to delta, we have taken del u del y equal to 0. At y equal to 0, we have taken t equal to tw, and at y equal to delta, we have taken del t del y equal to 0. So we can again see y equal to 0, u equal to 0, v equal to 0, y equal to delta, u equal to 0, del u del y equal to 0. At y equal to 0, t equal to tw, and at y equal to delta, t equal to t infinity, and del t del y equal to 0. Now if we integrate basically the momentum equation between 0 and delta, that means within the boundary layer, we can write 0 to delta, integral 0 to delta, u del x plus v del u del y dy, 0 to delta, g beta t minus t infinity into dy, plus 0 to delta, nu del 2u del y2 dy. And this integration, if we convert u del x plus v del u del y in conservative form, we can write del x of u square plus del y of uv. Entire quantity is integrated with respect to dy. G beta we can pull out of the integral sign, t minus t infinity dy. Here integration is nu del u del y. One is at y equal to delta, but y equal to delta del u del y 0. Then lower limit minus nu del u del y at y equal to 0. So this again we can write as integration, differentiation under the sign of integration, and this partial derivative we can write as dtx and u squared dy. Here after the integration it becomes uv, delta is upper limit, 0 is lower limit. But uv, when we integrate for natural convection, this integration will not produce any result, because at upper limit delta u equal to 0, and at lower limit 0, u and v both are equal to 0, we know very clearly. So this is equal to the right hand side equal to g beta integral 0 to delta t minus t infinity dy minus nu del u del y. So we can summarize this as ddx of integral 0 to delta u squared dy equal to g beta integral 0 to delta t minus t infinity dy minus nu del u del y at y equal to 0. And this is basically in natural convection scenario, we can call this as momentum integral equation. Now we look at the thermal boundary layer equation. There also we integrate the equation between 0 and delta u del t del x plus v del t del y integration dy equal to 0 to delta integration alpha del to t del y2 dy, and we can integrate term by term. So 0 to delta u del t del x dy, v del t del y we integrate by parts, and here we have written first function into integral of second function dy between 0 to delta minus derivative of first function del v del y into integration of second function, and this together integrated between 0 to delta. And this integral, when we evaluate this term, we can basically write as v is basically minus del u del x. So this integral we can write t, we can bring outside, and v is basically 0 to delta del u del x dy. So this becomes t infinity, this first term, t infinity into 0 to delta integral del u del x dy. V is basically minus del u del x integrated between 0 to delta. And this integral we can write as t, and del v del y is substituted by minus del u del x from continuity equation. We have written also invoking continuity equation. So this is 0 to delta t del u del x dy. This term comes here. So, and the right hand side is minus alpha del t del y, y equal to 0, because this is the lower limit. Upper limit is alpha del t del y at y equal to delta is 0. So lower limit we apply, and minus alpha del t del y, y equal to 0. And this we can, these three terms we can write as 0 to delta del del x of u t minus t infinity, very clear, into dy equal to minus alpha del t del y, y equal to 0. Again, differentiation under the sign of integration by applying Leibniz rule, we can write ddx equal to ddx outside 0 integral 0 to delta u t minus t infinity dy equal to minus alpha del t del y at y equal to 0. And if we define theta equal to t minus t infinity, then this integral becomes ddx integral 0 to delta u theta dy equal to minus alpha del theta del y at y equal to 0. And this is for natural convection situation is energy integral equation given by this expression. So we have to recall basically the momentum integral equation and energy integral equation. If we can solve these two, we will get the velocity field and temperature field. Now we can also define theta m, maximum temperature difference, is Tw minus T infinity. T minus T infinity is theta and Tw minus T infinity is theta m. So temperature distribution can be written as theta by theta m equal to T minus T infinity divided by Tw minus T infinity, and we have written it straight away as 1 minus y by delta square. Basically, we can take a polynomial and then satisfy these conditions at y equal to 0, t equal to T infinity. That means at y equal to 0, theta equal to theta m. At y equal to delta at the edge of boundary layer, t equal to T infinity, that is at y equal to delta, theta equal to 0, because theta is T minus T infinity. At y equal to delta, T equal to T infinity. So T minus T infinity definition, this will be now T infinity minus T infinity, theta equal to 0. And at y equal to delta again, del T del y equal to 0. That is at y equal to delta, del y of this whole, from this whole expression, we can write basically del T del y means del y of Tw minus T infinity into 1 minus y by delta square equal to 0. So this profile, when we take theta by theta m, is 1 minus y by delta whole square. This satisfies all these boundary conditions, all the physical boundary conditions. Now for the velocity profile, again we can go back to this basic schematic, and we can take a higher order polynomial a plus by plus cy square plus dy cube, and again the boundary conditions are at y equal to 0, u equal to 0, at y equal to delta also u equal to 0, outside the boundary layer there is no velocity. At y equal to 0, nu del 2u del y2 equal to minus beta into g Tw minus T infinity. This is the boundary in the simple boundary layer equation. Substitute y equal to 0, boundary layer equation for buoyancy driven flow, and then we'll get nu del 2u del y2 equal to minus beta into g Tw minus T infinity. At y equal to delta, del u del y equal to 0 at the edge of boundary layer. Now these conditions, first condition, second condition, third condition, fourth condition, if we substitute here, we will finally get a equal to 0, b equal to delta beta g divided by 4 nu into Tw minus T infinity, c equal to minus beta g by twice nu Tw minus T infinity, and d equal to beta g divided by 4 nu into delta Tw minus T infinity. Now this a, b, c, d, if we substitute here, we will get u equal to g beta delta square Tw minus T infinity divided by 4 nu into y by delta into 1 minus y by delta square. This becomes the velocity profile, which satisfies all the physical conditions. So now if we try to identify these terms, g beta delta square Tw minus T infinity and by 4 nu with their dimensions, like temperature difference is in Kelvin, beta is 1 by T, that means 1 by Kelvin, delta square is meter square, G is meter per second square, and nu is basically meter square per second. And we will see that this entire quantity, including constants, will be having the dimension of velocity. So we can write u by ux, which can be called also from here characteristics velocity. So u by ux equal to y by delta 1 minus y by delta square. So we simply just summarize these terms as ux and then write as u by ux equal to y by delta 1 minus delta square. So this is basically the velocity profile. And if this be the velocity profile, then we have to also basically we can spend little time to find out the location of maximum velocity. That means the y distance from the plate where the maximum velocity is located. So for that we find out dy of u equal to 0. We set this, and finally we get delta minus y into delta minus 3y equal to 0. This is very simple. We substitute the profile and perform the derivation, differentiation, and here y equal to delta, this is a trivial solution. So basically at y equal to delta by 3, we get the maximum velocity. So if this is delta, that means delta by 3, 1/3 delta, we get the maximum velocity. So Umax by Ux, if we want to find out, and substitute y as delta by 3, then we will get Umax by Ux, and here we can see Umax, this maximum velocity is 4 by 27 into Ux, and Ux is basically given by these quantities g beta delta square tw minus t infinity divided by 4. So that is the measure of Ux, and this is the measure of Umax, which is at a distance delta by 3 from y, we get the Umax. Now energy equation, that is basically we said that energy integral equation, we have to what we have to do. If this is the energy integral equation, now we know u and theta, we substitute u here, theta here, and we get the full form of the equation. So ddx of theta m, this is the theta velocity profile, ux into y by delta 1 minus y by delta square, this is u, dy equal to minus alpha theta m del y of 1 minus y by delta square. This is basically nothing but minus alpha del theta del y at y equal to 0. So we get after performing the integration, substituting the upper limit and lower limit, we'll get 1 by 30 ddx of ux delta into theta m equal to twice alpha into theta m by delta. So this is basically we obtained from energy integral equation. Now you look at the momentum integral equation, and momentum integral equation was given by this. So basically if we know u now, if we know t now, here t momentum equation and the energy equation are coupled, or temperature field is coupled, we have to know the temperature field, and then nu del u del y, so we can evaluate this. We are exactly doing that. The momentum integral equation, this is u squared dy g beta t minus t infinity dy minus nu. Here the right hand side is minus nu g beta 0 to delta t minus t infinity dy minus nu del u del y equal to 0. So minus nu del u del y at y equal to 0. And then again we perform these integrals, substitute for upper limit and lower limit after performing the integral, and we get this equation, which is given by 1 by 105 1 by 105 ddx of ux square delta equal to g beta theta m delta by 3 minus nu ux by delta. So this is a summary of basically the momentum equation or momentum integral equation. So from momentum balance we get this, and from the energy integral equation we get this equation, and we have to see how these two equations now can be solved. So those two equations given by 18 and 19, ux and delta are dependent variable and x is the independent variable. In the both equations we can see ux and delta appear. So ux and delta are dependent variables and x is the independent variable. To solve the above two equations, ux and delta are considered as functions of x. So ux and delta vary according to the following functions. We take ux equal to c1 x to the power m. M is not known, c1 is not known. We take a very general form of variation, ux equal to c1 x to the power m and delta equal to c2 x to the power n. c2 is not known, n is not known. This is also general form of variation. And then we substitute that u, which is c1 x to the power m, and delta, which is c2 x to the power n, in this equation and in this equation 18 and 19, and we get m plus n by 30 c1 c2 x to the power m plus n minus 1 equal to twice alpha by c2 x to the power minus n. We are defining this as equation 20, and from basically the this equation, which is outcome of momentum equation, we get twice m plus n divided by 105 c1 squared c2 x to the power twice m plus n minus 1 equal to 1/3 g beta theta m c2 x to the power n minus nu c1 x to the power m minus n by c2, equation 21 we are calling this. So equation 20 we are repeating. We have already found out m plus n by 30 c1 c2 x power m plus n minus 1 equal to twice alpha by c2 x to the power minus n. And equation 21 we have just derived. We rewrite that. Having done this, we try to solve for m and n, and then we analyze how the m and n can be related. The equations have to be treated in the following way. First, let us consider equation 20. If a monomial nonlinear expression is dependent on a variable, say x, that is equivalent to an expression independent of x, Then for universal validity of the equation as a function of x, the power of the nonlinear expression must vanish. Please read it carefully. If we divide equation 20 by its right hand side, then for the universal validity of the expression, we can say m, we just divide x power m plus n minus 1 by x power minus n. So we get m plus twice n minus 1 equal to 0. Rather, we divide the entire equation by the right hand side, but when we focus on the power of x and for universal validity of the equation as a function of x, the power of the nonlinear expression must vanish. That means then the power of x, which will be m plus twice n minus 1, should be set equal to 0. This we get from equation 20. I read this statement once again. First, let us consider equation 20. If a monomial nonlinear equation is dependent on a variable, say x, that is equivalent to an expression independent of x, then for universal validity of the equation as a function of x, the power of the nonlinear expression must vanish. And we get m plus twice n minus 1 equal to 0. Then we take up the next equation, which is outcome of momentum equation. Twice m plus n divided by 105, c1 square into c2, x power twice m plus n minus 1 equal to 1/3 g beta theta m c2 x power n minus nu c1 x power m minus n by c2. Now let us look at equation 21. Any number of terms with non-zero degree can combine to result into a single term, provided each of the terms has same degree. The degree of the resulting single term will be equal to that of other combining terms. Any number of terms with non-zero degree can combine to result into a single term, provided each of the terms has same degree. The degree of the resulting single term will be equal to that of other combining terms. This will lead to then twice m plus n minus 1 equal to n. This is 1. And another is twice m plus n minus 1 equal to m minus n. Any number of terms with non-zero degree can combine to result into a single term, provided each of the terms has same degree. The degree of the resulting single term will be equal to that of other combining terms. So we will get twice m plus n minus 1 equal to n, and twice m plus n minus 1 equal to m minus n. Twice m plus n minus 1 equal to n. Twice m plus n minus 1 equal to m minus n. And from here we get twice m minus 1 equal to 0 and m plus twice n minus 1 equal to 0. Just note that from equation 20 we also got this m plus twice n minus 1 equal to 0. And here also we are getting this m plus twice n minus 1 equal to 0. The conclusion derived from equation 20 and one of the two conclusions derived from 21 is the same. So now by solving this, we can get m equal to half and n equal to 1/4. So this is the conclusion, m equal to half and n equal to 1/4. So after having obtained m equal to half and n equal to 1/4, we can get a further reduced form of equation 20, and that is given by C1 into C2 square equal to 80 alpha 22, C1 square into C2 by 84 equal to 1/3 G beta theta m C2 minus C1 by C2 into nu 23. From 22 we can easily get C1 equal to 80 alpha by C2 square. Now C1 equal to 80 alpha by C2 square, we substitute in equation 23. So 23, wherever C1 is there, we substitute that by 80 alpha by C2 square whole square, first term C1 square, C2 by into C2 by 84 equal to 1/3 G beta theta m into C2 minus again C1 is 80 alpha by C2 square, 80 alpha by C2 square, nu by C2. And from here we try to solve for C2. And finally we get this expression C2 equal to after solving this we get C2 equal to alpha power 1/4 within bracket 76 by 80 plus nu by alpha and bracket closed power 1/4 80 alpha to the power 1/4 1/3 G beta theta m by nu square to the power minus 1/4 nu power minus half. So little bit rearrangement we do, and then we write C2 equal to 3.93 nu by alpha to the power minus half into nu by alpha plus 20 by 21 to the power 1/4 G beta theta m by nu square to the power minus 1/4. So this becomes C2, and then C1 becomes 80 alpha by C2 square, which can be again reorganized, and we can write 5.17 into nu within bracket nu by alpha plus 20 by 21 bracket closed to the power minus half G beta theta m nu square entire quantity to the power half. So C1 and C2 we clearly now write C1 as 5.17 nu within bracket nu by alpha plus 20 by 21 to the power minus half G beta theta m nu square entire quantity to the power half, and C2 is 3.93 nu by alpha to the power minus half within bracket nu by alpha plus 20 by 21 to the power 1/4 G beta theta m by nu square, this entire quantity to the power minus 1/4. So these are C1 and C2, and basically we want to get explicit way the expression for ux, characteristics velocity, and delta. Ux is given by C1 x to the power m, delta is given by C2 x to the power n. We have now obtained expression for C1, expression for C2, we have also seen value of m and value of n, and that we found out, if you recall, from our analysis, in a very general way, m equal to half and n equal to 1 by 4. So now we know m, we have n 1 by 4, c1, c2. So we can get expression for ux, which we have just written c1, whatever we have written here, into x to the power m means half, again delta equal to c2, whatever we have obtained as c2, enter c2 into x to the power n means x to the power 1/4, x to the power 1/4. So ux and delta we can write this way. Having obtained ux, that means the velocity profile and the growth rate of boundary layer, we will move forward to find out the temperature distribution and subsequently the heat transfer at the plate, at the vertical wall, at different locations from the leading edge. Rest of the calculations we will perform in the next class. Thank you very much. Thank you for your interest. Thank you.